Hey AP Stats, we are going to talk about Chapter 9, Sampling Distributions. So in this chapter, we're really going to emphasize the difference between a population mean and then a sample mean, and we'll do the same thing for proportions. So first off, that phrasing sampling distribution you'll see quite often in this chapter and then the future chapters. And we talked about today in the investigation where that usually means that we are taking a sample and then taking some summary of that sample. So like taking the sample mean and doing that over and over and over again, and we get all these different sample means and we look at how those means are distributed. So we're not just looking at raw data anymore. All right, so first up, how much do American households earn? The government contacted a sample of 113,146 households in March 2005. Their mean income in 2004 was 60,528. That 60,528 describes the sample, but we can still use it, but can we use it to estimate the mean income of all households? Okay. That's usually the process that we're going through. We have sample data and we want to estimate it for more people, bigger values. Okay. So we're going to investigate whether a number describes a sample or a population. So first off, a parameter is a number that describes the population. Okay, the P's always go together, which I think is very helpful. In statistical practice, the value of a parameter is usually not known because we can't examine the entire population. So the parameters include mu and p. Okay, so mu is the population mean and p is the population proportion. A statistic is a number that can be computed from sample data. Without making use of any unknown parameters. So in practice, we often use a statistic to estimate the unknown parameter. Statistics include x bar is our sample mean, and we haven't really seen this too much. P hat is the sample proportion. So the P with it's like a little caret on top of it, you call that a hat, so P hat. Right, the mean income of the sample of households contacted by the government was 60,528. The number 60,528 is a statistic because it describes a sample. Okay, statistic. What's doing? Which describes the sample. Sorry, that was weird. Okay. The population that the poll wants to draw conclusions about, this is usually something you want to be able to phrase in words, is though 113 million US households, the parameter of interest is the mean income of all the US households, and we don't know that. Okay, so again, you want to make sure you can understand just in words, the sample is a smaller subset of the population, and the population is, in this case, all US households, and we actually don't know that. Okay, so we're going to break up these future chapters almost in half, and we're going to do something for the means and then something for proportions. It's usually the same concept, but we have to handle them a little bit differently. There's different rules for means versus proportions sometimes. So we're going to kind of separate the chapters and deal with means and then proportions. So the mean, like the population mean, is denoted by mu. Okay. And the sample mean is denoted by x bar. Okay, we're going to keep going over and over and over on this notation, so you'll get the hang of it. Proportions, the population proportion is denoted by a lowercase p, and then the sample proportion is denoted by p hat. All right, so example 2, determine if the following are parameters or statistics, and we'll see how we can tell. For part A, a department store reports that 84% of all customers who use the store's credit plan pay their bills on time. So is that going to be a parameter talking about a population or a statistic talking about a sample? This is going to be a parameter. And there's one key word that we see that really helps you to note that it's a parameter. Do you guys see it? We've got 84% of all customers. It's not a sample of customers, we're talking about all, and that use the store's credit plan, pay their bills on time. So they would have information on all in that case, okay? All right, B, a sample of 100 students at a large university has a mean age of 24.1 years. Parameter or statistic? Hopefully that one was kind of easy to see. It's a statistic because it says it's a sample of 100. So if we're dealing with sample values, those are going to be statistics. Okay. Just a side note, in reading data and reading what they're giving you, we got 100 students at a large university had a mean age of 24.1 years. Does that seem old to you to have sample of students at a university, their age to be 24.1? Does that seem old? There's another key word in this statement that should help you to explain that. Do you see that? What happens at large universities? Large universities usually have graduate programs. So they have master's, PhD programs, and things like that. So at a large university, you have people who are doing extended education, not just undergrad. So that's why the age can get higher than like the 18 to 22, which you get for like undergrad usually. All right, so example 3, the Gallup poll asked a random sample of 515 U.S. adults whether they believe in ghosts. Of the respondents, 160 said yes. What's the proportion of the sample who say they believe in ghosts? Is this value a parameter or a statistic? Okay, so we'll start with, is it a parameter or a statistic first? We get it? It's a statistic, okay? We've got a random sample of 515 U.S. adults. So we know we're talking about a sample. So again, we got to start to get the notation down. So we're going to talk about a proportion. So if you look back up on the same page, if you're talking about a sample proportion, how do we denote that? It's a P with a hat, P hat. Okay, sample proportion. We have 160 said yes. So 160 out of the total 515. Okay. So we can divide that, then we just get 0.3107. Okay, so your sample proportion is 0.31. So some things that come up. So if a different sample was taken, or was chosen by the Gallup poll, it would most likely produce a different value. It'll probably be close to that one, but it'll be different. You ask different people, they could have different opinions. This is called sampling variability. Okay, this is going to be, oh, it's going to do that again. Sorry, sampling, I don't know why it's doing this. Variability. This is a key phrase that you will see throughout this chapter and the coming chapters, where we don't always get the same answer. And that's perfectly fine. If you ask a different group of people, you should get a different answer. Just like when you guys did the sticky note histogram on the board, did everybody get exactly the same answer? No, you basically had simulated 100 different heights of women, so your answers are slightly different, and that's totally fine. It would be so boring if every time you took a sample you got the exact same number as everybody else. There'd be no purpose in taking multiple samples. So sampling variability just means that the value of a statistic varies in repeated random sampling. Okay, so sampling variability is not fatal. If you look at the results of taking many samples, you would see that what we saw in the investigation. Take a large number of samples from the sample population. Calculate a sample mean, so an X bar or P hat, depending on what you're doing. Make a histogram of the values. And then examine the distribution of the histogram for the shape, the center, the spread, any outliers, deviations. Basically, that's that whole activity that we did with the sticky notes. We don't really want to do that every single time we have a problem. So we can use simulation to help us out with this. Okay, so because I was gone a bit, we didn't talk about simulation as much as I would have liked, so we're going to kind of pull in some more simulation stuff throughout this semester. Okay. So here's our example. Thousands of travelers pass through Guadalajara Airport every day. Before leaving the airport, each passenger must pass through a customs inspection area. Customs officials want to make sure that the passengers do not bring illegal items into the country, but they do not have time to search every traveler's luggage. Instead, they require each person to press a button. Either a red or green light lights up. If the red light shows, the passenger will be searched by a customs agent. A green light means go ahead. Customs officers claim that the probability that the light turns green on any press of the button is 0.7. We will simulate drawing a simple random sample of size 100 from the population of travelers passing through Guadalajara Airport. Okay, so we get that. As you pass through, you're going to push the button and it's either going to be red or green. Green means you go ahead, red means they search your luggage. Okay, probability it turns green is 0.7, so that means they're searching like 30% of the people. So that's our situation, and also says we're going to make a random sample of size 100. So kind of key things we want to keep track of. Green, 0.7. We're taking a random sample of size 100. Explain how you would perform this simulation using the random digits table for a sample size of 100 with probability 0.7. Okay, so random digits, we always have to figure out if we're going to use single digits or double digits first. So our probability is 0.7. What do we think? So with this, since our probability is 0.7, we can use single digits. So I'm going to choose to use single digits just because then I look at less numbers and I think that's easier, but it's not wrong to do double digits. Okay, you will probably get a slightly different answer. You're going to get a different result, but it doesn't mean it's wrong. Okay. All right, so I'm going to use single digits. Consecutive digits. So those are numbers that are right next to each other. So on the random digits table, okay, so 70% have to be green light. So I'm going to use 0 through 6, because that's 7 numbers, so 0 through 6 represent a green light. And so then 7 through 9 represent a red light. Okay, so then we usually would state where we're starting. In class, I do this a little bit different. So you're going to start on a certain line number. And I usually give that to you, okay? And then determine, if each passenger gets a red or a green light, okay, we're going to keep track until we reach 100. And what we're actually going to do is find the proportion. So it asks for this down here in part C. Find the proportion. A lot of times you're going to need to write that in your explanation of your simulation. So this problem, it just wasn't all written all together. So I'm just going to make a little note and find the proportion of people who get a green light. So basically what we're doing is seeing, is it really actually going to be close to 0.7? We're going to check it. Okay. All right, so carry out the simulation starting on line. What I've done in the past is every other row, I usually either assign line 125 or line 130. Okay, so usually I have you go every other row and do, so half the class is doing line 125, half is doing line 130. The reason I do this is because when you do it, then you get slightly different answers. All right, and then how you do this is basically, I don't want you to go like look at, let me just give you an example. Say we have that's just our numbers. And you know, you're going to go down the row. For each one, I don't want you to have to write down like 4 is green, 3 is green, 9 then is red, 0 is green, 8 is red. Because it's going to take you forever to write all of those 100 numbers down. Instead, all you need to do is look at, we're only keeping track of green, okay? What I do is then I look at the random digits and I look how many are in a row. I don't have one in front of me. I think there's 25 in a row. Is that right? They're in groups of 5. I think it's like 25 or 30 in a row. And I will mark then where I'm stopping. So there'll be a couple rows and then I put a mark where I need to stop. And so then I can just go through and count how many numbers are between 0 and 6. So I would just go through and go 1, 2, 3, keep going, 4, 5, 6, 7, all the way until I get to my line. That way I don't have to make like a table and keep track of all this stuff. Like you just mark your stopping point and then count them, okay? So the two different lines, and you can check this if you want to, but line 125, they get a sample proportion of 0.64. Line 130, you get a sample proportion of 0.66. So you just start on a different line, you just get a slightly different number. That's the only purpose in doing that. Oops, sorry, so those go down here. Proportions, and proportion 0.66. Okay, so then check what your neighbor got, because some people get it wrong. So you just got to check and see. And across the rows, they're going to be different. So what's their sample proportion? It's different than yours. The population proportion was supposed to be 0.7. So are we close to that? We're kind of close. I mean, we're in the ballpark. We're not exactly at 0.7, but it's pretty close. And then the key phrase here, if you have two proportions that they're kind of similar, but they're not exactly the same. It's not that anybody made an error. They're slightly different. What is that called? There's a keyword that I had you underline or highlight. You have different values. That's called, big keyword, sampling variability. Okay, make sure you know that word, sampling variability. Okay, and so I do want you to do this in your calculator because this is exactly what we did in the class activity. So we did the random norm. So this one we're doing it at 0.7. This is the standard deviation. I'm just giving that to you. I'll show you how to calculate it later. So grab your calculator if you don't already have it out. So we're going to do random norm, and this again you get to by math. Go over to PRB, probability, and then go down to random norm. 0.7, 0.046, we're going to do 100, and again we're going to send that to L1. So store it in L1. Okay, so go ahead and grab your calculator and do that. There's just going to be a whole bunch of numbers that are, and again, we're talking about proportion, so they're all going to be like 0.7, 0.6, 0.8, whatever, in that ballpark, 0.5. So that's what your whole list of numbers should look like. But what I want you to do is then draw a history, or look at a histogram. You don't have to draw it. So, and here in your histogram, I'm not going to tell you the window. Just do zoom 9, just to look at your sketch of your histogram. Okay, so you can see the shape. Okay, and then what I want you to do next is to find the mean of your L1. So you can do one variable stats of L1 to find that mean, or just do mean of L1 in your list, whatever you want to do. Go ahead and find your mean. So this is the mean of your sample proportions. Okay, so we generated all these sample proportions in the list. And then you can do one var stats of L1, and we want the mean from there. So the mean of our sample proportions. So this is how you're going to write that, and we'll kind of talk more about this notation in one class. But the mean, so mu, and then a subscript, we're talking about our sample proportions. So the mean of my sample proportions is whatever you got out. So your answers are all going to be different than mine because they were randomly generated numbers. So they should be something close to 0.7, but anywhere from like 0.68, 0.69, 0.7, 0.71, it's probably where they'll end up. Mine was 0.7004. But again, that's just from randomly generating numbers. Okay, so here in this histogram, shows the shape of the sampling distribution after doing this 1,000 times. So they got those sample proportions 1,000 times. So you can see what this would look like. Okay, so if we do this over and over and over again, and there's a couple things that we want to look at. So how would you describe the shape of this? And I'm just going to do bullet points here. So the shape, it's symmetric and bell-shaped. Something that we'll talk about in this chapter would be saying something like it's approximately normal. You cannot just say it's normal. That's like, I mean, it's literally like saying a 4-letter word in like the AP Stats world. You can't just throw like normal out there. It's literally written in the answer key of the test that if they just said normal, it's not full credit. You have to say approximately, so don't forget that. All right, the center, what would you guess the center is approximately? Can we tell where it's centered? It should be centered at 0.7. That's where our population was. Can you tell that it looks like here it's pretty much centered at 0.7, so it looks pretty good. The spread, we don't really have that much to compare it to other than what's in your calculator, that total spread. But here, can you guess? We're counting by 0.2s. Down here, so it looks like it goes from about 0.56 to 0.84, just like this min to max. And there doesn't look like there's any outliers or anything in there. Okay. So the official definition of your sampling distribution of a statistic, okay, it's very wordy, but we'll hear it enough times that it'll start to hopefully like resonate with what it means to you, okay? So the distribution of values taken by the statistic in all possible samples of the same size from the same population. Okay, we're taking all the same sample size from the same population. The key thing is here too, we're talking about all. So this is when we talk about a sampling distribution, it's like the perfect distribution, not just one that we can come up in class with, but even the one that we just saw up here, this is only for 1,000. So this is doing this like infinitely many times. You get like the perfect theoretical distribution because you have all possible samples. Okay, that's what we're talking about. And the sampling distribution is the ideal pattern that would emerge if we looked at all possible samples of size 100 from our population for the example above. Instead of having to perform the simulation every time, we can use probability and statistics to obtain exact sampling distributions. Okay, so there's like things that have come out over time that we just see general tendencies that they've kind of developed statistics for, so we don't have to do this whole simulation every single time. But this is what the sampling distribution, I would probably put this on a flashcard. This official definition comes up as like multiple choice questions. You'll see this. But it's the distribution of values taken by the statistic. So whether you're talking about a proportion or a mean. And it's in all possible samples. That's the key word there. Okay. Keep them the same size from the same population. So we'll talk more about that when I see you guys in class. All right, see you later.